worth pointing out. It's only for d is equal to 3 that you have this direct connection to photons and gravitons. So I will use periodic boundary conditions to start with. So first of all, if d is equal to 3 and alpha is equal to 0, I have the partition function of the Casimir effect, as I tried to show yesterday. And then I have to tell you what this additional observable here is. It's linear momentum in the direction, which is going to be the compact direction. So PD, when it will be relevant, will be minus integral d minus 1x pi di of phi. And if you express everything in terms of modes, so PD will be something like, so let me forget this prime because it's technical. It's, at this stage I take periodic conditions in all directions, and then P3 is really, it's D3, so it drops a K3 if you want. And in terms of the periodic modes, is this, it's this kind of object here. And then remember that there was this map which told you what it was in terms of the modes of the photonic E and H modes. In terms of the photonic E and H modes.
So I'm just confused by P, the I on the right hand side.
Which I?
The first line.
This one?
Yes. And on the left, I don't see.
So this is in the D direction. Well, of course, right, this is just XD. Because in the end, I'm only going to couple, of course, one can do more general things, but I'm only going to couple linear momentum in the direction that I'm taking smaller and compact. But of course, from the very start, you could look at all of them. And then there would be chemical potentials for all of them, and not only for this one, which is...
Glenn,
yes.
The D is the spatial dimension.
D is the spatial dimension.
But the integral for the Hamiltonian, you wrote D to D minus 1.
This at this stage should still be, let me think, okay.
Like this.
And here as well. This, of course, it depends if you are denoting D, the space-time or the spatial. And of course, later on, as you will see, when I take two directions which will be small, the continuous one will be D minus 1, and the discrete ones will be, there will be two discrete ones, one with time and one with space. So then it will be really D minus 1, that's kind of confusing. Of course, you are absolutely correct. Okay, what I was trying to say is there was this map on the level of oscillators between, so if you express this in terms of the oscillators for E and H modes that we discussed yesterday in the three-dimensional case, it turns out that, so there was this map between these oscillators, so you can re-express it in terms of creation of E modes and H modes, and it is really a kind of helicity operator, like Daniel was saying. So you see that this guy destroys an E mode and creates an H mode, and vice versa, and it's kind of dressed up with the K3 or that you need in this direction. But this turns out to be the good observable for modular invariance. Okay? And if you're just interested in temperature inversion symmetry, you don't need it, but if you want modular invariance, like in 2 dimensions, you need an additional observable, and that turns out to be the good one. But the question is what it is in terms of space-time electromagnetic fields, because you would think, naively, we were thinking that this was also linear momentum for the electromagnetic field. But if you re-express it in terms of the electromagnetic field, it turns out that there's one observable which is almost close to it, which is called spin angular momentum of light, and which is basically, it's the following object. So you look in any optic books like Mandel and Wolf or something like that, you look at spin angular momentum of light, And here transverse means that I am on the constrained surface, so I already throw away the parallel, like yesterday, the A parallel and the E parallel. So this guy, if you write it out in terms of modes, turns out to be almost this guy, but it will be this one divided by K. So it's not quite the right one that you need for the mathematical stuff that you want to do. But of course, it's easy to fix because, okay, this guy, I should say this guy, if you choose this component. It's the third component of spin angular momentum of light that will fit. So the one that will fit on the nose with this mode expansion is the following guy. So you can continue to call it P3, even though it is not P3. So it will be a kind of non-local observable, which is related to this third component of spin angular momentum of light, just by this non-local expression. And as we discussed yesterday in Fourier space, this is really like dividing by K. If you hit. Okay.
So, again about the notation. So the perpendicular symbol for you means...
it means many things. This is really reducing to putting this to 0 and putting this to 0. I'm not using this I will not use this in a consistent way, because there's many meanings to transverse. But here, it's really like in the sense of Helmholtz decomposition. You have a vector, you decompose it. If the thing is invertible into the transverse part, which you know contains the transverse photon and the longitudinal part.
But it doesn't refer to perpendicular to the boundary.
No.
Okay.
This is, and there is this tension between the two things. If you have boundary conditions, this, what I was saying yesterday, transverse electric and transverse magnetic, was with respect to the boundary.
Yeah.
And this is with respect to degrees of freedom in this sense. But, okay, but it's very easy in Fourier to implement. It is really putting this A parallel and this pi parallel equal to 0. And in reduced phase play means really solving the constraints and getting rid of that stuff. Of course, probably it means that if you would do this in bare state language, there would be a closed extension to this, which cancels the stuff that you have too much. But this we have not done. Is it clear? Okay. So this is a parenthesis. It's just to know what this precise partition function would mean if you would do it with photons. Right? I mean, it's this observable that you need. Of course, this is reverse engineering to some extent. Okay, so now I will do a computation that probably you have all seen in one version or another in a master's course, but I think it's useful to do it here because it's the simple computation in the large volume limit of the partition function. And the way I present it, it will be relatively easy to see how this changes if I take an additional direction to be small. So now I will be interested in canonical quantization. At this stage, so there will be nothing about modular invariance. So canonical quantization. I will take the chemical potential to be 0, and I will look in the end what happens in the large volume limit. So the easiest computation that you can do, in which, in fact, you have no divergences at all, if you put the system in a box by putting periodic boundary conditions in all dimensions, is to compute this object here, where you take the normal ordered Hamiltonian. So you forget about the 0-point energy just by choosing the normal ordering, and then you just compute that in a box with periodic boundary conditions. And then the Hamiltonian is of course in that case, I mean, I already said it, but in that case the Hamiltonian is just this discrete sum. So it's really, putting it in the box means that you don't have this continuum of oscillators, but you have discrete oscillators for each I, Ni, if you want. And you have this standard thing of quantum field theory that your field appears as this superposition, decoupled superposition of harmonic oscillators with frequencies given. Is it okay? And then you know that the partition function will be the product, because it's decoupled, the product of partition functions of individual harmonic oscillators, each coming with their frequency. So you really can use the simplest quantum mechanics thing. So, because then you have this basis, this tensor product basis in which everything is decoupled and in which you have a basis which diagonalizes each individual Hamiltonian. And then you just have to do the product of harmonic oscillators for all these n's. Is it okay? So in formulas, what I'm saying is that this guy is going to be the product of ni belonging to ZD, the sum of the occupation number for each of this system, and you get to do the geometric sum for each of these objects here. I mean, the easy, what I tell the students usually is do 2 decoupled harmonic oscillators and try to do the partition function of that. You find it's the product of the individual bonds, and here it's just the product for all of these n's. Is it okay? So, and then you sum the geometric series. Of course, you know that this guy is going to be 1 over minus epsilon beta omega ki. Right? And then comes the step, so then you say, but I don't want to do this product, because doing products, I take the log and I want to do sums. So I do ln of ZD beta is going to be minus the sum of this ni's minus this discrete sum of the log of 1 minus E beta omega ki. And then comes the step of, so you have regularized the system by putting it in the box and by putting periodic boundary conditions, but then you don't want to do sums because you are better at doing integrals, so you take the large volume limit, okay? And large volume, so you take Li large, which basically technically means that you go from the sum over the ni's to, you have to take this thing that you get from the change of variables. So the sum becomes the volume over 2 pi to the power d, and you get the integrals over the k. Is it okay? And then, so that's the step where you go from something which was defined on a torus, if you want, with periodic boundary conditions to RD back, because you just use this, also you can do Abel planar or something, you use this, just technically that's what you exactly do, okay? And you get this volume factor, so this is, this should be, yes, VD out of this, just because the decay, when you think how you go from the k's to the n's, there's a Jacobian, if you want. Okay, so, and then you go to spherical coordinates, because you can go to spherical coordinates because this only depends on the modulus of k and not on any angles. And then you get to use this formula that you teach your students when they have to do dimensional regularization, which is what is the volume of the sphere in d-1 dimensions, right? So because the result that you get when you go to spherical coordinates is Vd over 2 pi to the power d, the volume of the S d-1, and then you have this integral to perform, which is a single integral. You get a kd minus 1 from the Jacobian going to spherical coordinates, and then it's really beta k. So the sums has become this integral, and the only integral that is left is the radial, the integral over the radius. Okay? And this one, so in dimensional regularization, at least, or in, I mean, you don't need, this is the standard formula in terms of the gamma function. Okay? So that's the volume of the d minus 1 sphere. So this is the result that you have. And then you do a couple of changes of integration variables and one integration by parts to play with this formula here. And it turns out that if you do that, this one becomes 1 over d beta to the power d, gamma d plus 1, zeta d plus 1. You don't recognize it immediately, but you get an integral after a change of variables, which you recognize as the right zeta function, which appears up to some powers of gamma. Okay? And then you have to massage this result a bit. Probably all of you have seen this kind of computation in 3 dimensions, exactly, where you get zeta 4, because this is the standard blackbody result. Then you have to massage this formula, so you have these 2 gammas sitting here, so you have to use something which is called the reduplication formula to simplify that one. So that's one that you have to use, reduplication formula. That's one that you have to use, and then it's useful but not essential to define what people in the literature, in the mathematics literature, call the completed zeta function. So this is a zeta function that is accompanied by some factors of pi and some gamma in order, and this is the good combination. And you can also see it's a good combination because all identities, especially ones that we are going to use later, is much easier in terms of this completed zeta function than in terms of the standard zeta function, because of lots of factors of gamma and pi go away, if you want. So, and people use this, but it tells you, so if you then express your partition function in the large volume limit, you find that the result is going to be just this thing. So the volume that we have pulled out, beta to the power d, which comes from here, and all the rest were numerical factors, and you get this result. Okay, so you get this completed zeta function times the volume over beta d. This is exactly what it needs for this to be without dimensions, and you are happy. And then you look at what is this. So this is the scalar blackbody result in any dimension, and you look what it is in certain dimensions to recognize, to see if you recognize your standard thing. So for d is equal to 1, which would be the result in conformal field theory, it is this thing because psi of 2 is then exactly this thing. Okay, you have in 2 spatial dimension, you have a zeta 3 over 2 pi, and then you have the area over beta squared. And then the one that you recognize is the psi 4, which is pi squared over 90, which is the scalar blackbody result, L1, L2, L3 over beta 3. So this result times 2 is the blackbody, the standard blackbody in the large volume limit, because photons, you have twice this result. Okay? Okay, and then there's another nice computation that you can do, which is you repeat the whole thing, and you're not using periodic boundary conditions, but you are going to use Dirichlet conditions, just to see what it gives. And what you think is the result if you do Dirichlet conditions for that in the large volume limit? Mr. Chairman. So the result is going to be independent of the boundary condition in the large volume limit. So you think, there is twice as many oscillators if you do periodic boundary conditions than if you do Dirichlet. But if you go through it carefully, you will see that there is a cancellation of this 2 from another 2, which comes because the volume is also smaller. So it is exactly as it should be. And then this fits with, I'm not an expert in that, but it fits with a result from statistical physics, which says that in the large volume limit, things should not depend on how you choose your boundary condition. So at least in this small example, you can check that explicitly. Okay, so with Dirichlet, it's exactly the same. And this is what's no longer going to be true if we choose some dimensions to be small. Then everything will depend exactly on the boundary conditions that you're choosing. With Dirichlet boundary condition, same result. Okay, so that was the exercise. Now, how this appears from the path integral point of view. How would you redo exactly this computation if you do a path integral? Well, first you would start with something like that. You would time slice. So if you really wouldn't know anything, you would time slice this, or rather temperature slice this expression here, like you do when you do the evolution operator in Lorentzian quantum field theory, where you time slice. Here you have to slice the temperature, and you get the path integral representation for the partition function. So that's and what you get when you do it directly is, of course, you get first the Hamiltonian version, so the products over all of these points, dxa over 2 pi exponential minus s Euclidean Hamiltonian, and this action is like that, beta dx d plus 1 integral dx minus I p pi, the Euclidean in the time derivative, and if you do everything, you have plus h minus I mu pd kind of here. Okay, so where should I put brackets? Probably, well, there is one bracket like this, and this integral only goes over this part, because here the spatial integral is already understood, so it will be something like this. Okay. Okay, and now just sometimes it's more useful to use, so beta times mu is what I called alpha before. Sometimes one parametrization is more interesting than the other. This depends on what you are just computing. And what is interesting is that if you compute the partition function, yep.
The first integral?
That's the one over the Euclidean time. And it goes...
There is no d plus 1.
Yes, there is a d plus 1 because my x0 became xd plus 1. So that's similar to the question you had in this sense. No, and it is very nice. Why is it so really? Why is it nice? Because that's the next point. If you're computing the partition function, automatically the partition function requires in the path integral, there is a prescription for what path you have to take, and it's periodic in Euclidean time. So what is nice is that now all your paths are periodic in space-time and no longer just in space. And the periodicity in space-time is beta, the inverse temperature. So as usual, when you do this path integral, now suddenly space and time, which in this canonical thing were completely decoupled, they come on the same footing, in a sense, and especially if you integrate out of the momenta. So we had periodic boundary conditions in all spatial directions, but now we also have a periodic boundary conditions in the time direction. And you begin to see that there can be a symmetry when you exchange space and time, these circles, in fact. And this is kind of hard to see on the canonical quantization, but in the path integral, you suddenly see that all boundary conditions are periodic, both in space and in time. And then you go Lagrangian. So how do you go Lagrangian? You integrate out the momenta because it's quadratic in the momenta. And then the action that you get when you integrate out the momenta okay, and maybe let me, so the volume in Euclidean time is going to be beta times the spatial volume. So there is a space-time volume. And if you want to think of them in a unified way, if you had these periodic boundary conditions in all time direction, you also can think of beta as LD plus 1 because it's the periodic condition in this additional direction. Okay, so if you integrate out the momenta, what you are going to get is this Euclidean Lagrangian action, which is going to be 1/2 d plus 1 x Euclidean, and then d plus 1 phi minus mu d phi. So this comes from this chemical potential. So the fact that you have this chemical potential, all it tells you is that rather than having the standard Laplacian in Euclidean space, it's a little bit skewed, the Laplacian, because you have this chemical potential sitting there. But basically, you have the scalar field to compute just the Laplacian in Euclidean with only periodic boundary conditions. Is it okay? And so this skewed Laplacian in d plus 1 Euclidean dimension, this just means that you replace dd plus 1 by this combination here, and it's due to the chemical potential. But then, what are the eigenfunctions? So in this case, the eigenfunctions are 1 over square root of v e exponential a k x a, and now my a for a change, of course, before now runs from 1 to d plus 1, if you want, okay, all the small dimensions. So these are the eigenfunctions, and in this case, you are lucky that you know exactly the eigenvalues of the problem, because a torus is simple, and you have all of them completely. So the eigenvalues, lambda and a, are just 2 pi over beta n d plus 1 minus mu 2 pi over ld squared plus sum over I 2 pi and I over li squared. And then, if you know, of course, the eigenfunctions and the eigenvalues, you know that basically this Lagrangian path integral requires you to compute 1 over square root of the functional determinant that you have here. Okay, and this you can do because, so you know that in this approach, the partition function that you are computing is supposed to be, if you think of it discretized, the product over all of these n's, square root of 2 pi over lambda, because it's a quadratic integral, and you know that this is supposed to be the determinant of this kernel that you have in your quadratic Lagrangian, and for bosons, the right power is minus 1/2. Okay? Okay, and then you want to compute that, and in order to compute that, you define the zeta function of this problem. So if you want to do it correctly, which most often you don't want to do, you have to divide by something like in dimensional regularization to make the thing dimensionless. Okay, so you have to introduce a kind of mu, which is like the mu of dimensional regularization, so that you have a dimensionless determinant. And then you define the zeta function of this operator to be just the sum over all of these objects of these eigenvalues, the non-vanishing ones. And you also have this 2 pi mu squared to the power s sitting there. Okay, and then you have to make sense of this product here. And how do you make sense of this product? And now I am at stage. Maybe let me keep this one up. So then the next step is to check if you can reproduce the black body result like that. And this was actually done in a paper, in the first paper by Hawking on zeta function regularization. He did the scalar field exactly like that. And it is really extremely readable. Everybody is after that using this kind of presentation for this computation. And so I'm taking mu or alpha, which is the same thing, equal to 0, and I take the large volume limit again. And then I look what happens to my zeta function. And the zeta function, so mu is 0, and then becomes something like 2 pi nu to the power s, volume d over 2 pi to the power d. I again get this, if you want, this integral. The sums in the spatial directions become integrals, and there's only one sum remaining, which is the Matsubara sum over the time frequencies, if you want. Okay, so the only thing that remains is sum nd plus 1. Only time remains small if you compute a partition function. If you compute a partition function, time is small. You're not like in scattering theory doing also t goes at this coordinate tending to infinity. So it's not 0 temperature. This one stays small, if you want. Okay. So a partition function already means that you always have the time circle if you want. This is a small direction in your problem. Okay, only the time direction is small, and that's why this one stays discretized. And you have 2 pi over nd plus 1 divided by beta squared, and the other ones become continuous, and you have the whole thing to the power minus s. And then there is one step that you have to do. So there's, in this case, there is one divergence which is related to what happens when the Matsubara frequency is 0, because then this integral just diverges and you cannot do a lot. So you just remove that, you put a prime, and then that's done, or you do dimensional regularization or something like that for that. So you just remove the guy nd plus 1 equal to 0, and then everything is pretty good, if you want. And then you do a change of variables, and you continue, and in the end, because you see, if you do that, you can put the 2 and make the sum over n star only, and you begin to see the zeta function appearing already, again, the standard one. Okay. So what is going to happen if you do that is you do a change of variable, you massage the thing, and you're going to get, so Vd, and then the same kind of volume of the sphere discussion that you had before, 2 pi to the power d, lots of pi. You also get rid of a 2 pi of beta, which you pull out of everything, and then you change variables, integration variables. So in the end, you end up with something similar than we had before. Not quite the same thing. Over gamma of s. Okay, so this is what the zeta function turns out to be. And then you have to use that in S, there is, so 1 over gamma of S, you know exactly how it behaves. So it's S plus order of S squared. And remember that in this formula for the partition function, you're supposed to compute two things, zeta at 0. I hope I put it up. I put it up. Maybe I forgot to put one formula there. So let me add it now. So the partition function explicitly in terms of the zeta function is it's basically 1/2 of the derivative of the zeta function at s is equal to 0. And then you have to check if zeta is in 0 is 0 in order for the result not to depend on this regularization that you have chosen. So that's the formula. Usually you only give this part, but somehow you also have to check that zeta of 0 is 0 so that it doesn't depend on the regularization, kind of.
And indeed, if it does?
I don't know. So what usually happens, at least as far as I can tell, for instance, there was this long discussion. So all this is in flat space, so it's easy. And there was this long discussion in the physics reports by De Witt, where he was arguing that for the scalar field, you should use the conformally coupled scalar field in order to do something. And I guess this is related to that, because then you are back to that situation and things behave much better. I don't know, I'm not such an expert on that. I'm just telling you that in the cases that you can look on this tori, this is always true, so you don't worry. So the result is kind of this regularization independent from that regularization at least. I don't know. It's not I mean, you should ask somebody who is a zeta function expert and not somebody who pretends to be.
Glenn, so there you put mu is 0, you compute zeta of A naught S.
Yes, so this is the mu, this is the chemical potential, because in this case of only large volume, I don't need any, I'm not looking, because this one is I'm not coupling the linear momentum in this direction.
So that's for the mu, not for the nu, because...
Yeah, exactly, and that's very confusing, because, well, okay, my collaborators prefer to use mu for the chemical potential. I prefer alpha, but for some reasons mu is sometimes better. But then you are not, usually the parameter that you use in dimensional regularization to make everything adimensional is called mu.
Yeah, I know.
And
it's fine.
I called it mu.
It's fine for me if you knew. But mu still appears on the
Mu still appears, but mu doesn't appear here. Mu is equal to 0. And that's the 0 because the A. Okay.
Could you have written mu there? Yes.
No, yeah, you're right, of course. So this guy depends on mu, but this guy, okay, it depends on mu, and I'm putting mu equal to 0.
Okay.
So it's this guy which is 0, and here this is still depending on mu. Very good. So then it turns out that, and that's what I wanted to say, now this zeta function, which you can do by elementary methods, because you are in one of these rare cases where you know all the eigenvalues exactly, and you don't need to use any approximation methods. Then you check, because of that, because of this, at 0 it is 0, and if you compute the derivative, and you get this finite result. Okay, the derivative at s is equal to 0, you can see that all the others have no problems in s. The only, so the end result is that the guy at 0 is 0, and that the partition function turns out to be, if you massage everything, turns out to be psi minus t. So you have to compute this derivative with respect to s, put s is equal to 0, put 1/2. You only have to put the derivative of s here, because otherwise all the rest vanishes. So it's basically everything that is there at s is equal to 0, except for this guy that you massage. Okay, I can show you the detail. I mean, of course, it's if you do it as a course, you have to. Okay, so the result is this result, which is very similar to the result that we had by canonical quantization, so you are kind of happy. The only thing that is different is that it's psi minus t and not psi of d plus 1. But then the whole trick about this, zeta function computation is that when you do it like that, you end up in the wrong part of the complex plane where your zeta function is not defined by the series you think it is defined. But you know that the analytic continuation of the zeta function has very nice properties, and one is this inversion formula. You have to use this inversion formula, which for the zeta function, which brings you back to the parts, or to the good part of the complex plane, if you want. And the whole magic of analytic continuation of this zeta function stuff is, so somebody has to give you these properties of the zeta function to bring you back to the good part of the complex plane. So this is the usual thing, sum of the integers being -1/12, you know, the standard stuff. So this sum is not well defined, but then you regularize it like that, and you bring it back, and then you get the -1/12. It's the same thing here. Okay, there are of course experts on this, but this is how it works when you do. This is what you have to do, this, and what is nice about this completed zeta function is that this reflection formula, which is the key in analytic continuation, is very simple in terms of the completed zeta function, and much simpler than it is in terms of the standard zeta function, where there's lots of factors of pi and gamma floating around. So this is the guy that you have to use, at z is equal d plus 1, and then you have shown that your path integral gives, in a very nice and covariant way, the same result that you had by canonical quantization, but of course you have to, the price to pay is this zeta function technology. Is it okay? Okay, oh well, you will not see any gravitons, but okay. Then there is something more that we need, which is the Casimir energy on a d minus 1 cross S1 LD. Okay, so I mean, what I've shown you in this lecture is nothing. I have shown you the black body result in 2 ways, how to compute it, but it's of course a complete standard result. But it's interesting to see it in that way, because then the generalization to more small dimensions is just almost technical. You just have 2 sums and only d-1 integrals, but it's the same zeta function that you compute, and you have a double sum in terms of a single sum, only in Matsubara. Okay, for the Casimir energy, the problem, so you have this Hamiltonian, and if you do not choose normal ordering, so you have this kind of things to compute. And you see that the 0-point energy for d spatial dimension is something like, so you have to compute this thing at 0 temperature. And you see that you have a very similar problem where instead of having the products of these eigenvalues, now you have the sum of these eigenvalues with 1/2 to compute. Okay, that's the kind of divergent expression that you have to compute. And either people have done really, they have put the system in a box and compared what happens if you take Minkowski space and then the space between the plates and subtract one result from the other and then stay with a finite piece. So that's one way of getting a finite result for this object here. And the other way is again to do zeta function renormalization or regularization of this sum. So that's the analog of the 1 + 2 being -112. Okay. And that's the one I'm going to use. And by very similar, so you define, instead of defining the sum of the 1/2 of omega, you put the power -s to the thing so that it converges, and then you do analytic continuation of the result that you are going to get. Let me not go, so in fact, if you do the zeta function, let me just say what happened. The zeta function regularization of this sum, you will see as compared to the computation before, it's the same computation than before, basically, up to some details. The only thing that is changing is that d goes to d-1, because you only have, now you have one small spatial dimension and all the rest large, because to get a Casimir effect, you have to have boundary conditions in space. So that's one. D goes to d-1, beta, which was LD + 1, you have to replace it by LD, the length of the small dimensions. And the difference is that S, you have to go, S goes to S -1/2, because that's what you have, because you have to do the square root of k squared. That's what omega is. So that's related to that. If you do that computation in the same way than before, the Casimir energy for periodic boundary conditions of a scalar field with periodic boundary conditions in only one dimension has exactly the same numerical factor than the black body result. And there is, on top of that, just the thing that you need to make everything dimensionless. So, and then you compare, and that's what lots of people have done. So this is a complete low temperature thing that you do. This is the leading contribution to the partition function at low temperature. You see that up to something which is fixed by dimensional reasons, the factor here, all the pi's and the 2 and the zetas, if there are, is exactly the same than in the black body result, if you compare these two situations. And this is kind of at the heart of this Cardi formula, where you relate what happens at low temperature to what happens at high temperature. Because in some sense, so the same numbers that I had put up appear exactly here for the Casimir energy. So I started at 10, right? So I have a bit more time. Okay. But this, of course, is slightly different, right? You can see that. Okay, and then you can do two small dimensions. If you do two small dimensions, you are now looking at your scalar field in space-time where you take only the d minus 1 dimensions large, you take one spatial dimension small, and if you are interested in computing the partition function, the temperature is always small. Okay, it's always a circle, as I've seen. So you have two circles, so you have a torus here, and you begin to see that there can be a symmetry in this system when you exchange the role of the small spatial dimension with the small time dimension. And modular invariance has to do with that, playing with the two circles, the two periodic boundary conditions that you have, and switching these things around, and at the same time switching low and high temperature, as you're going to see. Yes?
Confused by the power of the...
Okay, so here is the volume of the large spatial dimension that remain, which are d minus 1. Okay, you are right, it's wrong, of course, the power, because this should be d. And because the energy, it's not dimensionless like the other absolute. So I have really, people are careful, it's great. I wish I could say the usual stuff that I'm putting this arrow in to check if you are, but it's of course not true. So, okay. So two small dimensions is in space-time you are looking at this thing here, right? And you do the zeta function again, and the only thing that is going to change for this, and now look, you keep the mu, because the mu is a kind of non-trivial twisting of this S1s. So if you don't have mu, then you really have that. If you have the mu, then you have a more general torus, not really the one which is like that, in a way that one can make completely precise. And as Nicolas was saying, there also should be a nu, but now I don't write the nu, because nobody ever does the nu. In fact, you just... So, well, only the people who are doing it rigorously. So now, the thing that factorizes in front of everything is the d minus 1 dimensional volume in the large direction. So that's the one that you pull out, which would be area in the case when you do d is equal to 3. And then you have two. So this is because this d minus 1 sums become integrals. And now there is really a d minus 1k over nothing. And you have a double sum, and d plus 1, and d. You have to do again the prime, and the eigenvalues. So you don't only have the Matsubara frequencies, but you also have discrete frequencies in the small spatial direction. I LD over LD ND squared plus the large remaining directions, and I runs from 1 to d minus 1, the whole thing to the power s. And then you repeat the computation of the partition function, and in that case, you are going to find the following thing. So it's interesting to organize your alpha and so alpha and beta, you can reorganize them in the way that people parameterize a skewed torus, which is you define this modular parameter to be tau plus I beta over LD, and you can just at the moment think of this as just a complex change of variables from your alpha and mu, from your beta and mu to these variables, and then you write the partition function, and you do the same computation, in this case zeta function, by using the correct reflection formula. And the most compact way to write everything is the following expression. So it will be over 2 LD d minus 1. Now it has really to be d minus 1 because it has to be without dimensions. Then you have a 1 over tau 2 to the power d minus 1 over 2. So this tau 1 and tau 2 are just the real and the imaginary part of the modular parameter. And then you get this completed Eisenstein series if D is bigger than 1. And the result, so this completed Eisenstein series is almost like a zeta function, except that it is a completed zeta function. So it's the same decoration factors of gamma and pi, which makes everything easy. And then there is a double series. And this is a real analytic Eisenstein series, which is really given like that. It's a double sum where you are not summing over the thing when both integers are 0. Or sometimes you denote this by that, minus. So that's the same thing than the 0 that we deleted before. There is a certain power of tau 2 in the denominator, in the numerator, and then it's nd plus 1 plus tau nd modulus squared. Okay, that's a real analytic Eisenstein series, and why people like it is because it's modular invariant. What does modular invariance mean? It means that this object is invariant under this symmetry. Tau goes to A tau plus B over C tau plus D, where A until D are real, are integers, sorry, and you have this determinant condition that this guy needs to be 1. Okay, this object here is invariant, but the partition function is not just this object here, but it has an extra power of the imaginary part of the modular parameter here, and that's why the result will be only modular covariant and not modular invariant, but that's still good enough for you to relate low and high temperature to the power d minus 1 ln zt of tau. Okay, so that's the modular invariant covariant partition function that you are going to compute. And then you can have, so this result is valid for d strictly bigger than 1. And also I should say that this modular invariant real analytic Eisenstein series is not the ones that you find directly in most books on modular forms, because you find usually a holomorphic version of that. This is not holomorphic. It depends on tau and tau bar, because there's the modulus squared, which is there. There is a version of that, which is really holomorphic, and that's what appears in most of the discussions on the mathematical side, but of course this has also been studied in great details. Real analytic, not holomorphic in that case. And then maybe my last remark is that you would think that for d is equal to 1, you just use this and find the modular invariant partition function of the free boson in 1 plus 1 dimensions. It's a bit more complicated, because in this case, for d is equal to 1, this series does not converge and is not a good series. So you have to do a longish discussion. And this is the discussion that is done in Itzig-Zuba or something, or also in Polchinski, to show how, it's called, I think, the first Kronecker limit formula, to show how, if d is equal to 1, the real thing that you are getting, if you are really careful, is, so you would think naively that you get this, if you put d is equal to 1. But that's not true. You have to do it carefully. And what you get when you do it carefully, and you can do it by hand also, but you can also look in all of these books, but it's kind of hard sometimes to understand the logic. You really get this thing here, which is the two-dimensional result if you do it really. But it's not direct to get it as a limit of the higher dimensional result. To some extent, the higher dimensional result is easier than the two-dimensional result. And as I was saying, so this is the Dedekind eta function, and this is the stuff that you get from the particle when you have periodic boundary conditions in it. Okay, maybe let me stop here.
Questions?
Yeah, so I mean, in a gravity context, there would be an interpretation of what it means to take modular images of your partition function. They would be interpreted as some instanton-like things that have an interpretation as Euclidean black holes. Is there something similar in this context when you take modular images? That this is some.
Well, this is just a boundary picture. You see, this is just the scalar field. So
Sure. But I mean, are you again?
Okay.
Are there instant? I mean, you just have a scalar field, but you also have non-trivial boundary conditions.
Oh, okay. Yes. Okay. Very good. Yes. No, you're right. There is one way to see this, which is one method that I have not yet talked about. You can also derive this result in a third way. So now you can do canonical quantization, and there's a third way to do this stuff, which is this world line Schwinger proper time heat kernel approach. If you do it in this approach, which is in fact the most powerful approach, and which is the one which is, of course, the mini version of string theory, if you do it there, you rephrase your problem as the partition function of a particle, or not the partition function, as the heat kernel of a particle in d+1 Euclidean dimension. And it turns out that if you compute this heat kernel by path integral methods, and you have a circle, you have to take into account the paths that wind around the circle.
Yeah.
And this gives exactly this other sum and this other thing that you have. And this would already be if you do the black body result by this method. You have the particle that winds around the circle. So if that's the instanton, that would be the analog of that. Okay. So you do have this picture, but you have to do world line. And I'm not sure that I have time to talk about that. Okay, everything takes time. But this is the method where modular invariance is the clearest, in some sense. Because in some sense you can see without computation. Because here you first do the computation, and then you look at the result, and you see that there is this symmetry. But sometimes symmetry you want to understand before you do the computation, not after. And in this world line you can see it if you treat the torus in a correct way. But this is, nevertheless, it's not gravitation, it's purely, it's in this approach that you have at least something similar.
Questions? But so again, so you mean that you remember for this zeta 0, you mean that you prefer to take some conformal case? That's what people say usually? Or this is related to conformal anomaly?
Yeah, I would say that usually people like stuff better which is conformal, in lots of contexts. There has been this, well, I can show you the plates where they are discussing that. So in his physics report, the old one on quantum fields in curved space, DeWitt, he knows the boundary conditions for electromagnetism, he's discussing perfectly conducting ones. Then he's trying to understand why the scalar field is working or not working, and why is it depending on the regularization. And in the discussion he says, the special feature of electromagnetism is conformal invariance. That's what he's saying. So this is, and then he's saying, but if we want the same kind of good results for the scalar field, we have to take the conformally coupled scalar field. This is much better. And then there's this discussion of the improved energy momentum tensor that is by Jackiv and Cartan and these people. Everything is conformal. So even scalar fields in curved space, if you look at it, people usually do the conformally coupled scalar in curved space. Maybe it's related to that. I have not checked that, but it could be. But they look at that.
Thank you.
You said that you took directly boundary condition, and now it's periodic boundary condition in this more direction. And so you said that for large volume it doesn't matter, but here
No, here it absolutely matters. Here I take periodic, but I take periodic for in 3 dimensions for a special reason, because I've shown that perfectly conducting is in that case is equivalent to periodic for the scalar in the one small dimension. So with that, I am discussing photons in the Casimir box. So you can check. The only thing that you have, you put d is equal to 3, you put LD is equal to 2D, which was the separation of the plates, and then the partition function that you are getting is exactly the ones of photons in this Casimir box. So it's the partition function of the finite temperature Casimir effect, and also of gravitons if you choose adapted boundary conditions. So somehow what was nice is you bring back the problem to scalar field but only in this particular case, I would say. Otherwise, probably you have to be. But we were kind of surprised that it was, this is the easiest way. So you look at these big books on the Casimir effect, finite temperature Casimir effect. They give the partition function in all details. And kind of first mapping it to a periodic scalar gives you the result much faster, I would say. Yeah, but you have to do this trick on the oscillators to map to systems one to the other. This is probably our only contribution to the field, I would say, because this field is studied in all detail, also heat kernel methods. There is books and books on